So then I'm coming to the final little bit of this, and that is the real goal. If you could pull it off, it would be brilliant, right? But it's not as far advanced, and that's nuclear fusion. Whereas those fission reactors rely on you breaking apart a nucleus and releasing energy, a fusion reactor relies on you fusing nuclei together and releasing energy. And the way you do that is to take tritium and deuterium and you fuse them together, and it makes a helium-5 nucleus, which then it breaks up to give you a helium-4 nucleus and a neutron. And the energy released in that is nearly 18 million electron volts for those 5 nuclei, those 5 protons and neutrons being fused together, compared with the 8 MeVs or so that are released when you have a fission reaction with uranium. So this is a much more effective source of energy if you can make it work. There are, and I'm going to show you, it has worked and it is known that it will work. Here we have this process. The way we extract energy from this is that we take the neutrons, and the neutrons hit blankets around this reaction, and they transfer their energy and heat up water again, and you get, again, all the recipes for driving turbines to give you electricity. Now, there are one or two, shall we say, small technical difficulties in doing all of this lot. The first is that tritium is not naturally occurring. So you have to make tritium. Tritium is made in some reasonable quantity in CANDU reactors, where you have deuterium as the coolant in the core of the reactor. But you also can make it by taking this neutron from this reaction and making it hit lithium-6. There's a release of energy there of 4.8 MeV, but more importantly, it changes into helium-4 and tritium. So if you can make this thing go, you actually get a lot of energy out. You can breed your next tritium that you can then put back into that reaction. Okay? So this is a very sustainable way of going forward. Now, what are the advantages? Well, I've told you what they are really already. In the currency of the world's energy consumption, the current world's energy consumption, there's 60 billion years worth of deuterium in the seawater. There's 800 years of cheap lithium in the Andes, in salty brines there. There's 30 million years of lithium in the seawater. Remember, these are really the fuels that you need, because the reaction is going to strike lithium to produce you new tritium. So you need the deuterium out of the sea. So you've got an infinite supply of materials if you can extract them and if you can make the fusion reaction work. And you get no waste and you get no CO2. Now, why do I say you know it's worked? Well, it has worked. In 1997 in Culham, where the Atomic Energy Authority, was a lab that the Atomic Energy Authority is responsible for, built I know what I forgot to tell you. I forgot to tell you one rather important thing. Let's go back 2 slides and then I'll come forward. The only problem with this is to make these deuterium and tritium collide together, they have to be moving at very high speeds. They have to be at an effective temperature of about 150 million degrees centigrade. So this is rather warm, right? But that's the way you overcome their natural ability to repel one another. So you have to be able to contain them at 150 million degrees in what's called a plasma. And that's what happened in Culham, in a tokamak, where you have lots of magnetic fields that hold these charged deuterium and tritium ions contain them in those fields. And inside this tokamak here, in the middle there, they reached 150 to 200 million degrees centigrade. And this is, and runs on that experiment. At that time, they were able to run this machine and get out of the machine, from that fusion reaction, about 15 megawatts of energy in the neutrons. They actually had to put in 25 megawatts of heating power to warm that plasma up to 150 degrees centigrade, 150 million degrees centigrade. So it wasn't efficient in the sense that it was only 2/3 efficient. But that reaction has been shown to exist, and you can make it run for longer, for 4 or 5 seconds, but at a lower power output. Nowadays, with what we know about these things, taking those results from column, you can predict that you'll be able to go up to this sort of level for this 5 seconds or so, and get up to the same level, beat that record, but for a longer sustained period of time. You know you can do it. In principle, that reaction can work. In principle, you know how to contain it in a tokamak. So, here are the issues. You've got to learn, however, to control that plasma. You've got to make sure you can build materials. So here we are for people who like doing materials science. Construction can withstand the neutron fluxes that they have to, which are, in the lifetime of one of these plants, these neutrons will bombard every atom in the blanket that's absorbing them. It'll knock every atom in that blanket off its lattice point, somewhere between around 150 times in that lifetime. So in order that the material is not going to just collapse in a heap of dust, right, you've got to be able to make materials that will actually withstand that neutron bombardment. And there are ideas and clear ways that you've got to do it, but you've got to develop them to make it happen. You've also got to make sure you can produce this tritium. You produce it in that blanket, and then you have to suck it out and then be able to contain it and put it back in again. That's not an easy thing to do. And the problem at the moment is the way of controlling this turbulence in the plasma is to make the plasma very big, which makes the power plant very big, which is actually a problem for costs and for construction. So the principle is there, but in practice there's a lot to do. Here's how one's going the next step forward. There's a big tokamak, you can see the similarity to the previous one, is being built in the south of France at Cadarache by this group of collaborators, and it's due to start in 2025. And it is supposed to put out 500 megawatts of power, not the 15 we just saw, 500 for long times of the order of 400 seconds, not the 5 seconds. And it's supposed to produce, first of all, an amplification. You're supposed to get this 500 megawatts for pumping in 50 megawatts. But the final goal, and I'll show you that in just this next slide, is that you hope you'll be able to make it self-sustaining, a self-sustaining plasma. Here's the construction site in Cadarache, and this is where the tokamak will be standing when it's finished. These are the assembly buildings. This is an enormous expanse of plant for building the the coils to produce the magnetic fields for the tokamak. It's well underway, but it's a very difficult project to pull off. But it will be the next step in making neutron fusion either a possibility or something you have to forget about. This is the reason why it's so important. Here you see the power output from fusion modeled in that plant. And what you see here is the power as the tokamak is turned on. Up steadily goes the power in this coming out of it to around this 500 megawatt level. But most importantly, this is the power that you're needing to create the plasma. When actually you turn it on, you're putting in somewhere like up to 70 megawatts of power. You drop it to 50 megawatts of power, and then eventually you drop it to 0, and you see this hardly changes. If And that's from the knowledge of the science of those plasma machines, those plasmas at the moment. So that would be the case where you had a self-sustaining plasma that would then run on forever, giving you out 500 megawatts, or until it had used up appreciable amount of the tritium that was inside it, and then you'd stop it and you'd restart it again with a new shot of tritium. That's the hope for the future in fusion. How does it all fit into the timescales that we've been talking about this afternoon? Here you can see that we're doing, this is really modeled a little bit on Britain, but on Europe in general. Here we're going to start building a new wave of EPRs, or light water pressurized water reactors. We're doing lots of research, fusion research and general research to be able to push this forward. We'll start start deploying, we hope, fast reactors. These are generation 4 fission reactors from somewhere around 2030 onwards. And then we'll prove that we can get first fusion electricity somewhere around 2045 to be able to begin possibly a generation 1 fusion reactor somewhere around 2050. So that fits you on a roadmap, basically, to how you'll supply this nuclear energy, which I think is going to be absolutely essential as a real component to helping us solve the energy and the climate problems of the 21st century.